Thank you very much, Peter, and it's great to be here. Last talk before cocktails. So just a little bit of background. The talk is FPGAs in the data center and at hyperscale, and I was thinking about this, and it's interesting because we talk about FPGAs in the data center, and actually they've been in the data center a long time. Wireless, wired communications, wireline networking, all large homes to massive quantities of FPGAs that have shipped over the last couple of decades are all in data centers. So I think we actually are really talking about, when we talk about the data center, we're talking about computing and the new ways that FPGAs are being applied. And I wanted to talk a little bit about, the whole concept of hyperscale and why this is important, to me, at Nimbix, is Nimbix has been all about the driving the vision for reconfigurable computing at hyperscale. The notion of FPGAs purpose-built, for specific workloads so that we can process information faster with the new types of workloads that we're seeing across the globe, AI being obviously one of those, and we'll talk about that in a second. Since our inception, really back in 2010, this has been an area that we've been really trying to pioneer, and in the spirit of the OpenPOWER ecosystem. Obviously, a lot of the work that's being done in OpenPOWER with CAPI Snap, we've been involved with, but also just FPGAs in general. So we'll talk a little bit about that. Okay. So, you guys are, well, real quick, how many folks are hardware-centric, consider yourselves hardware people? Okay, quite a bit. Any software? Okay. So we're gonna go up the stack, but the idea here is I'm actually a hardware guy myself and love hardware. And part of the challenge of getting to large quantities, large volumes of any kind of hardware is finding the applications that will consume that hardware at scale. And it seems like my adapter is not happy here. Let me try a different one. I think it's just the connector. All right, let's see if we can get lucky here. Okay, so if you guys remember, those of you that have been around the hardware for a while, in the 80s and 90s, it was a lot of logic. We talked about, I used to sell actually for Texas Instruments the just standard logic, right? Discrete logic components, and we'd have boards full of discrete logic components, and the competitive devices were FPGAs that could suck all that up into a single chip. So you did that for integration, and it was important, obviously, in communications, industrial, and embedded applications. And over the years, we've seen the technology advance dramatically. With SerDes in the FPGA, you've got, massive numbers of gates and logic. You're putting entire systems on these chips, processors in these chips. And, but you tended to think of these as devices that ultimately ran in typically very customized applications and in low volume. So we think about what are the things that start to unlock the potential of FPGAs, as we continue to advance in our technology. So again, it's kind of taking this concept of looking at FPGAs historically, you think about ASIC emulation, the applications that I mentioned, areas that you guys are all very familiar with. And one of the challenges in the data center is how do you put these, multi-$1,000 devices in servers where you're constantly pushing component costs down to, very inexpensive things so that you can scale out those volumes. And so those seem like they're incongruent. But part of what's really interesting about the time we're in right now with pushing through, especially around OpenPOWER and OpenCAPI and mechanisms and frameworks that help democratize access, is driving the numbers of applications that can actually consume this hardware to quote unquote commoditize it to some extent. So let's look at hyperscale deployment and cloud evolution. And actually, if we think back to the beginning of Amazon, which is really the sort of the parent of cloud computing, it was really ushered in with open source virtualization technology and quasi leftover computing from e-commerce, right, that was now being repurposed and sold as computing cycles, initially targeted in a very developer-centric way, right? Lightweight applications, web services, things like that. And this was breaking the notion of enterprise computing where you're standing up, very feature-rich machines, and the hyperscalers, Amazon in particular, Google, Microsoft, were stripping everything out and focused on, again, commoditized volume. But what we've seen in the last several years, and Nimbix has really been sort of, really pushing the envelope on the type of class of infrastructure that that we host in our cloud. But you're now seeing that from all the major providers around the globe. And that is evolving because the demands of the type of work that they're putting on are changing. They're focused not just on the developers of lightweight applications, but they're recognizing that what enterprises and people need to compute are different classes of workloads that have very sort of sophisticated requirements from the infrastructure itself. And then you've seen the evolution to heterogeneous computing with GPUs and FPGAs. So for those of you that have followed what's happened over the last 10 years, let's say with GPUs, it's been pretty fascinating to watch, and I expect the actual same thing to happen with FPGAs. And that is, you take this graphics technology and you find a few applications where they used sort of the actual architectural advantages of a GPU for vector processing to speed up HPC applications as one example, or real-time ray tracing, very specific applications. And it didn't take long before the number of use cases and graduate programs, graduate students writing code in CUDA to target this hardware. And NVIDIA did a nice job of capturing this and building cards for the data center, and now you're seeing that go. And I remember in 2010, I was at the supercomputing conference in New Orleans, and it was almost heresy to talk about putting things other than lots and lots of CPUs in a big cluster. And now you can't find a supercomputer that doesn't have a GPU in it, or a cloud on the planet that doesn't have GPUs as a large-scale deployment. And we're just at the beginnings of this same trend with FPGAs. And the reason why we're at the beginning and we're seeing this trend now is that there's a need for both performance from a lot more people and agility from these people. So it's not just in the realm of academics and research, it's in the realm of day-to-day enterprise computing that needs this type of processing power. And that is, goes from deep learning and AI to large-scale computation, so traditional HPC, and HPC algorithms that can, be accelerated in these new types of architectures and these new technologies. And then we're also seeing this convergence around, again, hyperscale, right? The need for the agility to where as one company, you don't have to build these monolithic systems. You can actually leverage computing power of other providers in the space and leveraging on unique capabilities and architectures from those providers. So one of the things that I find interesting is that you've got these kind of mega trends happening in the background. You've got demands from the market. And when it comes to FPGAs, there's been a challenge. And we've been working on this now for literally, I think, 9 years, right? Our first FPGAs in our cloud were actually supported with, if you guys remember, if you've been around it, the Convey computer hybrid core systems that had Xilinx FPGAs in them as a co-processing engine. It was a pretty monolithic design on a standard one-use server, but very specific, customized architecture, and they were, hard to program, and that's something that's been a challenge with FPGAs. And when you look at, the methodologies, and we saw some of this with, and some of the great advances in the work with frameworks like CAPI-Snap, moving to OpenCAPI, which are helping democratize the ability to get code into these hardware systems. But you take it going back to RTL, to actually being able to synthesize from IP blocks that are already off the shelf, which is helping shrink design cycles, to all the way to high level languages and the ability to use tools to actually take existing code and actually target that to the devices. So we're seeing a movement from these monolithic self-contained tools environments where an FPGA developer is in a lab on a machine with a board and a set of expensive tools, to we're starting to see that open up into more collaborative cloud-based environments. We're seeing, historically, long design cycles, get compressed. We're needing to get to market faster with these new types of codes and being able to iterate, break things, and because we're shifting the way developers do it, it's not as big of a crime if they do break things, right? Because they didn't spend $20,000 on boards and tools and so forth to try to get their software working. Testing on local hardware, and then also being able to expand that outside of the local environment. And then moving from customized hardware to more open and standardized hardware. And this is everything that you're seeing here, at the OpenPOWER Summit, as well as cards like the Xilinx Alveo, which has created, their own branded form factor and create some standardization for the market to actually target versus, again, a lot of highly differentiated systems that, again, just prevent sort of the scaling process from happening. So the next challenge, of course, is when you compare to traditional FPGA software development, the demands that are going on in the rest of the market around software and applications that are being consumed by large organizations. And they're needing these applications to be runnable on-prem, on their existing clusters, on their cloud partners' infrastructure. And over the last decade, we've seen lots and lots of software companies build software that's distributed in traditional ways. We've seen them build scaffolding to actually deploy it in an automated way on a cloud provider of their choice, but it tended to be glued into either an Amazon or a Google or a Microsoft, for example. And increasingly, organizations are wanting that software to be deployable anywhere. And part of what the technology that's enabling that to happen is the proliferation of containers. And what I'm going to do is transition a little bit about, kind of this look at getting FPGAs to scale in the data center, and then also some of the ways that Nimbix is working to help enable that, democratize access, and speed up time to accelerate both software development as well as deployment of hardware. And part of, again, the way that this ecosystem is evolving is the use of containers. And what we're finding, and certainly Nimbix has been supporting for several years, is the use of this type of technology to create FPGA accelerated software, package it so that it's deployable anywhere and runnable on the bare metal FPGA hardware. And the benefits to this are a couple-fold. One is that you're generally using FPGAs because you want performance. The other thing is when you're trying to scale out the hardware, you don't necessarily want to be limited or constrained by the hypervisor that's running, underneath, or have to pass through the hardware and do a lot of kind of unique things in the infrastructure layer to actually pass through that hardware. And actually, a good case in point of that is when Amazon's release of the F1, which has been fantastic for the market. I think Alibaba has FPGAs as a service offering as well. But ultimately, what customers want to do is be able to consume the software applications at scale. And so containers has become a mechanism by which many software companies are now packaging their code and deploying them across environments. And it enables applications to work both in a virtualized environment as well as a bare metal environment. So let's look at kind of the flow of that from an application ecosystem standpoint. In the container world, you see from kind of left to right, formats, registries, platforms, and runtimes. And so in formats, obviously the most prolific is Docker. In the HPC community, Singularity has become popular as well. From a registry standpoint, Docker Hub, you have Google, there's, NVIDIA has a container registry. I'll talk to you in a minute about HyperHub. And then platforms, obviously, are container-native platforms like Kubernetes, Mesos, and we're seeing, obviously, Kubernetes proliferate immensely, especially in the deep learning side of things. Jarvis, the platform that actually powers the Nimbus Cloud, is a container-native platform that's been focused on accelerated computing in HPC. So, very tightly coupled workloads and workflows, as well as, obviously, FPGA and GPU-powered workflows. And then runtimes, obviously having the actual container runtime to actually execute the applications. So if you're an ISV, a software developer, you're concerned with building, distributing, and monetizing the applications, and you're choosing your delivery mechanisms. Well, part of getting to hyperscale is being able to have those applications be consumable anywhere. And so containerization is a very important technology enabler to helping speed up the time to deployment of new infrastructure and then the software that can actually consume that infrastructure. So what Nimbix announced actually last week as part of our effort to support the ecosystem of acceleration is what we call HyperHub. And this is essentially a branded application marketplace that is open, that we've been curating over many years, but we're now actually going to be opening it up and offering it for developers, ISVs, enterprises to be able to park their applications, to be able to deploy them on any infrastructure. And when you use, this is for essentially the distribution, deployment, and running of the workflows on any application. So it's important, it's not just a container registry, right? Container registries will contain all the bits of the application, but it also includes the elements that describe the runtime environment. So you're actually executing the application. When you launch it, when you click on an app card, you're not just pulling a container, you're actually launching the work on the infrastructure. This includes native accelerator support for both GPU and FPGA based infrastructure. It's obviously purpose-built for more traditional high-performance applications, but obviously for accelerated infrastructure is one of the key attributes of it. And then importantly, it supports through Jarvis XE, which is the software sort of operating system that powers our cloud, but is now also something that we are selling to enterprises to run their on-prem infrastructures, is the synchronization of this marketplace. So when it comes to FPGA accelerated applications, the ability to propagate those to more than one cloud or to any infrastructure, including your own data center, is really important. So when you combine sort of the HyperHub with the Jarvis XE ecosystem, which today is over 1,000 applications and workflows across both the HPC and accelerated ecosystem, it's a platform for containerized continuous integration and development. So the idea for our CAPI Snap work, for example, is that Alex in France can develop his application in CAPI Snap, publish it. That application can run on the Nimbus Cloud, but it can also then, through HyperHub and Jarvis XE, propagate to any other CAPI Snap enabled or powered infrastructure. So what our goal here going up the stack from a hardware standpoint is to actually put work on the infrastructure. So part of why we build incredible hardware is so that we can actually put it to work. And what we want to do is democratize access by reducing complexity. So the idea for us is to create more software-oriented, software as a service-oriented, and platform-level access for developers. So we want to be able to onboard these new accelerated applications, going back to, for example, the CUDA and GPU. CUDA was different because most people had CUDA on their laptops because they had a GPU in their graphics card in their PC or their laptop. In the case of FPGAs, it's a little different. And so while you may be able to do some basic tool development, in this environment, you can actually go end-to-end all the way to infrastructure. And then from an actual software application developer, it provides a pathway to distributing their applications and software globally, and also monetize that IP. So if you are developing a new acceleration OpenCAPI or CAPI Snap enabled application, you can actually propagate this throughout multiple infrastructures in a very easy way. You can build once and adapt it to run on any cloud infrastructure that supports the actual hardware that your application targets. And then finally, importantly, for FPGAs, we have digital rights management technology built in, which supports bit stream protection, which is an important actual additional element in the case of FPGA accelerated workloads. And this works will be supported both for kind of the traditional PCIe-based, acceleration as well as the CAPI Snap and OpenCAPI support. Onboarding applications, we've tried to make very easy, and whether you use containers or using containers or deployed that way now, it can be done through compilation of Git source and directly depositing that into a container, or simply pulling in containers that you may have already created, as well as some documentation around creating the metadata that you might use to describe the actual runtime environment for the end consumers of those applications. And then I've included a couple of links for the work we're doing with Xilinx Alveo accelerators, as well as with IBM on the CAPI Snap. So with that, thank you very much for your time, and I'll happy to take any questions if you have any. You ready for cocktail? Oh, okay.
So on your Jarvis XE, so the one thing that I find interesting, we've got a lot of diversity partners here and for OpenPOWER as well, is the ability to take something that was developed either on-prem or in the cloud and move it both directions.
Yes.
Right? So if I have something I developed in the cloud, I can move it back to on-prem, or if I'm limited with my on-prem infrastructure, I can go capacity on managing the cloud. For a university, what is the licensing type model that you provide on the Jarvis XE environment to help them get going?
Yeah, so we don't have a specific different licensing model of Jarvis XE for universities other than our traditional university discounts, but I think it's an area where we are actively pursuing technology collaborations. So where there's interesting ongoing work that's sort of pushing the envelope on new infrastructure technology, we are motivated to invest to support that, and can make that make that software available in those cases. And we would just take that on a case-by-case basis. And we do actually have a form where we do allow researchers and academia to submit proposals, and then we come back and do everything from discounted stuff to free and sponsored type work as well. Yes. So we have the Nimbix Cloud supports workloads globally out of data centers in North America. HyperHub and Jarvis XE is available globally for deployment in any data center or any cloud provider.
We are looking at the OpenCAPI contact channel. So that would be one of the university will join. So might be,
Yeah, no, we'd be happy to chat. Yeah.
We want that on Power 9 and OpenCAPI.
Yeah, and by the way, and that's an important thing that I didn't, I guess I mentioned it a couple of times, but our platform and part of what we're about is heterogeneity. That goes for CPU, it goes for accelerator. We're not biased towards, x86 or GPU. And what it's about is about targeting the workload to the right infrastructure and allowing the platform to place that work on the most well-suited infrastructure. So, and Power, by the way, the Jarvis XE and HyperHub supports Power 9, Power 8, the prior generation, as well. And then, we'll continue to be innovating in partnership with IBM on all the sort of futures as well. Right? Thank you, guys.